So I know what you're all thinking. You're thinking, Prof. Ross, how do we do current division in the phasor domain? Well, today's your lucky day because that's exactly what I'm going to show you. So here's our current source. Making it easy for you, throwing a current source and then asking you to do current division. So it saves at least a couple of steps. Oops. 60 millihenries here, 40 ohms here, 120 ohms here, 12.5 microfarad here, and then there's this V0, the voltage across the inductor. And there's node A. There's given I sub G, this independent current source here is 0.5 cosine 2000 t amps. They want you to find V0 of t. So this voltage across the inductor as a function of time. So the strategy we're going to use specifically is current division. Okay, then Ohm's law on V sub 0. All right, so we want to transform to the phasor domain. We're going to redraw this circuit in the phasor domain just to make it clearer what's happening. So transform to phasor domain. So first thing we can do is do the phasor transformation for I of G. So I phasor is going to be the magnitude, peak magnitude, and then the phase angle, which is 0. Okay, there's no phase angle in here. It's just omega t, plus nothing. Okay, then we need to calculate for the these reactive elements, the capacitor and the inductor. We need to calculate the impedance for those guys. So the impedance of the cap, and these are so I is a phasor and Z is a phasor, and sometimes I forget to draw the arrow on top of Z, because Z is always a phasor. Yeah, anyway, so this is minus J omega C, so this is minus J over omega is 2000, and C is 12.5 microfarad. This is going to be minus J 40 ohms, right? And the impedance of the inductor, Z sub L, is J omega L, so it's J 2000, 60 times 10 to the 3, minus 3, 60 millihenries. It's J 120 ohms. So we can redraw the phasor domain circuit, which is, we're just changing the capacitance and the inductance values to their impedances instead of their capacitance and inductance. So this guy was J120, and this guy is just 40, because for resistors the impedance is the same as the resistance, no change. And this cap was minus J40. So observe, this inductor has a positive imaginary value, J120, and the cap has a negative imaginary value, so minus J40. So that's yeah, just keep that in mind. And so we can use current division, all right? So current division at node A. So you could even say at A. So this I is, so we got to label these. So let's call this I1, all right? I1 phasor. and call this I2 phasor. So this, we're in phasor domain now, so this should be capital I phasor. So this I phasor is from the source, is coming over here and getting split, you know, this way one way and this way two way. So we want to solve for I1, so we're taking I and splitting it, and we put the impedance of of both branches on the bottom. So 120 minus J40, that's this branch here, and then this branch over here is 40 plus J120. And then we're solving for I1, so we put the opposite branch on the numerator. And then that's where you need to make sure your calculator can do these, because if you're doing these manually, take a long time, okay? And we haven't even gotten that complicated yet. So make sure you can do arithmetic and matrix operations, for that matter, on complex numbers, right? So I do that, punch my buttons in my calculator thingy, and I'm going to get, I'm going to get, I didn't plug in, okay, I should plug in I, right? So this is going to be I, and all of this stuff here is going to be 0.5 minus J 0.5. That's just this stuff. And then you can plug in I. So we have I in phasor. I'm in polar. I is a polar form phasor, and these impedances over here were rectangular form phasor. So we've got a little of both. So there's I, and our total impedance value. It's not really an impedance right now because it's current division. It looks like an impedance, but it's not. It's just it's just a complex number. It means something, but not exactly impedance. Anyway, 0.5 minus J is 0.5. So this is rectangular and this is polar. So in your calculator, make sure that they are of the same form. Like in my calculator, polar and rectangular look the same. They're just comma separated numbers, So I have to be careful that they're either both polar or both rectangular or whatever you need to do for your calculator. But anyway, just beware of that. And you're going to get 0.25 minus J, 0.25 amps. So that's I1. That's the current through this side here. Oh, V0 is still here. We could label this V0 phasor. Okay, now let's just do Ohm's law on V0, right? So V0 phasor is I1. Phasor is the impedance of the inductor. This is just Ohm's law on the phasor domain, right? So this is 0.25 minus J, 0.25, and then the impedance of the inductor here is J120. Okay, J120. So punch those buttons and you get 30 plus 30J volts. So 30 this way and 30 this way. And it's a 30, and this is a 45 degree angle in here, the angle. And if we calculated this length, it would be 42.43 with an angle of 45 degrees. So this value here is 42.43. So what can we say about that? It's an inductor. The current has I'm not sure we can say a heck of a lot about it, really. The current also has a 45-degree angle, which is a little bit odd. Yeah, it's something I'm going to think about later on my own. But anyway, there's something interesting here that I think I'm learning something here. But anyway, I'll spare you guys that. So this is V0 in phasor domain, but they're asking for V0 of t, V0 in time domain. So V0 of t, we can take this phasor back apart, and it's going to be 42.43 amplitude cosine. Same freak, 2000 t, same freak as the original signal, and 45 degrees volts. Okay, it's a pretty easy problem.